Okay, in this video, we're going to learn how to figure out the empirical formulas and explain how to do that with different compounds. We're going to determine the empirical formula from either a percentage or a mass composition. So most of the examples here, you start with a percentage of it's the opposite of figuring out the percentage. When you have the formula and you figure out the percentage, we're going to go backwards. We have the percentage and we're going to figure out what the formula is. Okay, so explain the relationship between the empirical formula and the molecular formula of a given compound, and determine the molecular formula from an empirical compound. Okay, so empirical compound consists of the symbols for the elements combined in a compound, and the subscripts on that compound has the smallest whole number mole ratio of the different atoms in the compound. And for an ionic compound, most of the time the formula unit and this empirical formula are the same. But for molecular compounds like the hydrocarbons and different things, the empirical formula, it doesn't always end up being the molecular formula. And for example, this dibromine gas is BH3 is the empirical formula, but its actual formula is twice that, so it's 2BH6. Okay, so it actually exists in nature as 2BH6, but you can see the ratios of the boron and the hydrogen are 1 boron and 3 hydrogen. That's the empirical formula. That's the lowest ratio of those two atoms together. So we're going to do some calculations of empirical formulas. So when we give these, we're usually given the percentages. And then we're going to take those percentages and pretend we have a 100-gram sample of that to make it easy. Then we're going to calculate turn those percentages into grams. That's all we do. So if the percentages are 78.1 and 21.9, we just take those percentages and literally just turn them into grams. We pretend we have 100 grams. So in that sample, we would have, just to make the math easy, it could be any number, but just to make the math easy, we have 78 grams of boron and 22 grams of hydrogen in our 100-gram sample. The next is the mass composition of each element by dividing. We want to figure out how many moles there are in each one. So for the boron, we have 78.1 grams of boron, and the molar mass of boron is 10.81, so 78 divided by 10.81 gives us a little over 7 moles of boron. Do the same thing with hydrogen, and we get 21.7 moles of hydrogen. Okay, so we figured out how many moles. We went from grams to moles. We figured out how many grams. Started out with grams, then we changed them to moles in each one. Okay, because that's what the empirical formulas are. The molecular formulas are the mole ratios of those elements in a formula compound. So we have 7.22 and 21.7 moles, respectively, of boron and hydrogen. Okay, so to find the empirical formula, you take whatever is the smallest mole of those two. In this case, it's boron, right? So we divide everything by the smallest mole of whatever compound we have. So in this case, we're dividing both by 7.22, and we get a molar ratio. Of course, we're going to get 1 on the boron, but the boron to hydrogen, when we do that, the 21 divided by the 7, we're going to get almost exactly 3. And in rounding and experimental errors of a compound, the mole ratios consist of numbers, close to these. So we're not going to, it's not going to come out perfect every time, but it will come out to be, sometimes, most of the time, it comes out to whole numbers, and we just ignore that if it's close to a whole number. But if these numbers if any of these mole ratios end in, like, say that mole ratio instead of 3 was 3.5. So if it ended in 3.5, then that means we had half a mole there. So we don't need half a mole, so we got to multiply everything by 2 to get rid of that half a mole. So in that case, we would have had 7 moles of hydrogen and 2 moles of boron, if that's the way it came out. Or if another thing that sometimes comes out, it comes out as if it came out to 3.33. like had a third of a mole. Then we'd multiply that by 3, and we would multiply everything by 3, and we would get 10 moles of hydrogen and 3 moles of boron. So we want it all to be that. So if it comes out in, if one of the mole ratios, when we do this, when we divide by the smallest one, and it comes out to be either a half or a third, or sometimes it comes out to be 2/3, 0.67. 1/3, 0.33, or 0.67, you want to multiply everything by 3. If one of the moles comes out to be 0.5, you want to multiply everything by 2. Okay, so another problem here. We'll try this one. So we've got these 3 things here. Find the empirical formula of the compound. This is a typical problem that you have for these empirical formulas. Just give you the percentages, and you want to go back to the formula. So we have the percentages. This is what we know. What we don't know is the empirical formula. We're trying to find the solution. So this is the kind of the way it goes. We change the percents to mass, easy. Then we change those grams, the masses in grams. We change those grams to moles. And then we divide by the smallest number of moles that we have. We divide all of them by the smallest number. Whatever the smallest mole we get when we do this, when we change the mass to moles, whatever the smallest one we get, we divide all of them by that. And the smallest one, of course, will have a ratio of 1, and then the other ones will be some multiple of that. So we'll go through this one. So we have sodium. We get 32 grams of sodium. Sodium is 22.9. We get 1.4, a little over 1.4. The sulfur, 22.65 divided by 32, less than 1 mole. And the oxygen was 44, so we got almost 3 moles. Okay, so which mole are we going to, we have these 3 mole amounts, 0.7, 0.14, and 2.8. And you can kind of get a feel for this one if we, these are all kind of multiples of each other. But we're going to do this, we're going to go through the procedure here. And we're going to do the smallest whole number ratio of the atoms. So we have this 1.4 moles of sodium and 0.7 moles of sulfur and 2.8 moles of oxygen. So we're going to divide everything by the smallest number here, the 0.703. So we do that. We get almost 2 here for the sodium. Of course, we're going to get 1 here for the sulfur, and we get almost 4 here for the oxygen. Now these numbers don't end in 0.5 or 0.67 or 0.33. So, and they're pretty close to, this is pretty close to 2, this is pretty close to 4. So we're just going to go ahead and round those up to 2 moles of sodium, 1 mole of sulfur, and 4 moles of oxygen. So an empirical formula would look like this. Na2 for the 2 moles of sodium, 1 mole of sulfur, and 4 moles of oxygen. We put the subscripts there to represent, in this formula, we have 2 moles of sodium, 4 moles of oxygen to 1 mole of that. So this is sodium sulfate, the SO4, of course, turns into the sulfate. Okay, so the empirical formula always contains the smallest possible whole numbers that describe the atomic ratio. The molecular formula is the actual formula of the compound. Now, sometimes these are the same, but sometimes they're different. But the molecular formula is always a whole number ratio of that. So it's the empirical formula, times 1 if they're the same, or times 2, or times 3, whatever we need to make it so that the molecular formula, whatever we need to multiply the empirical formula by to get the molecular formula. Yeah, so they may not be the correct number of coefficients, is written as follows. So you have to multiply some number times the empirical formula equals the molecular formula. These are the molecular weights of each one of these. And the formula mass is the same thing. Determine the molecular formula of a compound, you must know the compound's formula mass. That's usually given to you. They give you the formula mass of the compound, and you pretty much have to have that given to you, or to find it in an experiment or something like that. Okay, so dividing the experimental formula mass by the empirical formula gives the value of X. So if we did an experiment and we found the formula compound mass, then we divided by the empirical mass, we would give that value of X, how many times greater it was. Compound's molecular formula mass is numerically equal to its molar mass, so compound's molecular formula can also be found given the compound's empirical unit, its molar mass. Okay, so what they're saying here is they give you the molar mass here, right? So P2O5, that's the empirical formula. We found that from the compositions, right? Did all the compositions, we found the ratio of phosphorus to oxygen was 2 to 5. Okay, but our experiment showed that we came up with a molar mass of this compound of 283.89. So what's the compound's molecular formula? Well, it could be this, right? It could just be this, or it could be a multiple of this. So how do we figure it out? So we want to figure out the molecular formula. We know that it's a multiple, the molecular formula is a multiple of the empirical formula. So to figure out what that multiple is, we take the molecular formula mass and divide it by the empirical formula mass. So in this case, the molecular formula mass is 283, and the formula mass, the same thing. They're just, this is the atomic mass units from the periodic table, grams per mole. These are the same things. And then we have to figure out our phosphorus, right? The phosphorus was almost 31, oxygen 16, and the empirical formula mass, when we take 2 phosphorus and 5 oxygens, okay, we get 141.94. So this is the empirical mass is 141.94. And we're going to figure out what it is, we know that we have to take the compound mass, the mass that we found from the experiment, and divide it by the empirical mass, the 141 we just found out. So we get almost exactly 2. Okay, so that means that we have to multiply each of these subscripts by 2, and the compound's molecular formula is going to be the P4O10. So it's going to be twice as much. See, it's the same ratio here, as it's 2 to 5 ratio here, but the actual compound is 4 and 10. That's what it's actually found in nature. Okay, so this is the empirical one, twice as much, gave us the molecular one. All right, so that's the end of the show. See you tomorrow in class.